Now let's look at one of the most common configurations for op-amp circuits, and this is called the inverting amplifier. And you will see variations of this type of circuit used in all different types of applications. So what is an inverting amplifier? Well, let's go first and let's analyze this, and let's find out what the relationship is between the output voltage and this input voltage of V sub S with this circuit. So in this case, I'm just going to call these resistors RF and RS, not give them a specific value. Let's solve this symbolically. And what we're going to do is we're going to apply the three rules. So, first of all, I know the input currents will be equal to 0. I also know that the voltages at the two inputs must be the same because I have negative feedback, a path from the output to the inverting input through that resistor. So, looking at this, if these two potentials are the same, I know the voltage at the non-inverting input is equal to 0. It's grounded. Therefore, I must also have 0 volts at the inverting input. Now, this is, of course, just the virtual short circuit, but because the non-inverting input is grounded, you will see this is called something slightly different. This is called a virtual ground. At the inverting input. So that's 0 volts, but not because the inverting input is connected to ground. It's 0 volts because of negative feedback and the infinite open loop gain of the ideal op-amp model. And so your virtual short circuit causes that to be equal to 0 volts. Given this, I can now go through. Let's define some currents through these resistors. Really, the only node I can write a KCL equation for is the inverting input node. I don't want to write one for the output node, don't need it. And so in this case, this is Vs. And so what we get here is that Vs minus 0 over Rs must be equal to 0 minus V sub O divided by RF. And now I can rearrange terms for this, and what we will get is that VO will be equal to minus RF over RS times Vs. This is the equation for our inverting amplifier. Now, why do we call it an inverting amplifier? Well, first of all, we note the minus sign in this term here in the center. This term we give a name to. This minus RF over RS is the closed loop gain. In other words, this is the amplification factor of this op-amp circuit due to the negative feedback of the formed by this resistor network. Now contrast that with what we defined earlier, the open loop gain. The open loop gain is the amplification factor without negative feedback, without any way of connecting the output to the inverting input. Okay, now you'll also see this closed loop gain represented as A sub CL as opposed to A sub OL. Closed loop gain, open loop gain. Okay, so Here we have the closed loop gain, but this is the closed loop gain for this particular configuration. Different op-amp configurations will have different expressions for the closed loop gain. But for the inverting amplifier, this is what we get. Now looking at this, let's plug some numbers in. Let's go ahead and let's let RF equal 2 kilo ohms. Let's let RS be equal to 1 kilo ohm. Therefore, VO will just be equal to minus 2K over 1K times VS will be equal to minus 2VS. So in this case, I've got a closed loop gain of minus 2. Now notice this is not infinite. It's in fact determined by the values of those resistors. And this is what is really powerful about op-amp design, is I can go through and I can select a gain value based strictly on the component choices I make. So this gives me a value of 2 based on the fact that RF is twice as large as RS. So the open loop gain is very, very big. But as long as I can create a circuit with a closed loop gain that's very small, I can basically ignore the open loop gain. The closed loop gain is what's going to dominate. So what do I get if I were to plot this? Let's say my input was a sinusoid. Let's say Vs was a sinusoid over, and I just plot this with respect to time, and it has a maximum amplitude of 1 volt. So I'll hit the peaks and the valleys at plus and minus 1 volt. What's my output going to look like? Well, it's equal to minus 2, so VO is going to look like this. It's going to have maximum value of plus 2 volts, a minimum value of minus 2 volts. But notice because of that inversion, when I hit a maximum positive input, I hit a negative maximum value output. So in effect, the input and the output are both sinusoids, but the output looks like a sinusoid that's 180 degrees out of phase. So I have an output that's 180 degrees out of phase, if you think about this from a trigonometric point of view, or it's inverted with respect to the input. Hence the name, inverting amplifier. So I get an output signal, which in this case has twice the amplitude of the input signal, but also gets flipped because of that negative sign and inverted. So it's an inverting amplifier, hence the name. Now note, I can pick different values for RF and RS to get different values of closed loop gain, different magnitudes. What is the smallest magnitude of closed loop gain? Well, the smallest closed loop gain magnitude in this case occurs if RF is equal to 0 or RS is equal to infinity. So remember, VO is equal to minus RF over RS times VS. So if I make RF 0, make it into a wire, or make RS infinity, open circuit, then my output voltage becomes equal to 0. So in this case, the closed loop gain, the magnitude of the closed loop gain will just be equal to 0. So think about that for a moment. Look at the circuit. If RS were infinity and that were an open circuit, well then clearly the input voltage can't get to the op-amp input, and so all we have here is that I've got 0 volts here, and then clearly there's no current flowing across that resistor. You know, 0 is equal to 0 plus 0 volts minus V over RF. It's just a 0 all the way across. So I'm going to have that equal to 0. Or I can leave the resistor here and I can short together RF. Well, in this case, if this is 0, that's 0 volts. It's the same wire, and once again the output's 0 volts. So either way, the output voltage is just equal to 0. ACL is equal to 0. Okay? So I can go all the way down to a amplification factor that's actually less than 1 or even actually equal to 0. So really I could build this thing to be not just an amplifier, I could make it into an attenuator where the output would have a smaller magnitude than the input if I chose the correct resistor ratios. Okay? Now, having looked at this amplifier circuit, I want to look at this from a totally different way. So here is, once again, our inverting amplifier circuit. Now, you guys hopefully are following the whole idea behind the 3 rules of op-amp analysis, but I want to show you an example that illustrates that really the 3 rules are nothing magical, they're nothing new. They are actually nothing more than the regular nodal analysis techniques we already understand. So I'm going to reanalyze this circuit, and instead of this being an op-amp, I'm going to replace that op-amp with a dependent voltage source. So let's go through, and I'm going to rework this problem in such a way that we're going to assume you never even heard of what an op-amp was. Instead, I'm just going to say, that's just a dependent voltage source. Let's do that, because I want to illustrate something about the analysis of these circuits. What if I had this? So in this case, I'm going to go and I'm going to treat this circuit as if the op-amp is nothing more than the very simplified model we talked about before. I've just got a couple of wires in which the voltages appear, and then I've got a dependent voltage source that's connected to the output, and AOL times VP minus VN is the expression for that dependent voltage source. So if you had never heard of the 3 rules of op-amp analysis, or if you'd never heard of op-amps at all, I would ask you this. Work this problem for me, get a value for VO, an expression for VO, and then let that open loop gain term go to infinity. So let's do that. Let's go ahead and let's see what we get out of this. So in this case, here's my VN, here's my VP for my inverting and non-inverting input voltages. And now let's go through and let's solve this. Okay, now once again, we're not going to make any assumptions about the 3 rules. So looking at this, clearly VP by inspection must be equal to 0 volts because, of course, the non-inverting input's connected to ground. So in this case, I'm going to go ahead and solve this using nodal techniques. That's a defined node, so I'm certainly not going to write an equation at this output node, but I can certainly still write an equation here. So what I get is that Vs minus V sub n divided by 1,000 is equal to V sub n minus V sub o over 2,000. So I just wrote a KCL equation for my inverting input node. Now we also know that VO is equal to AOL times VP minus VN. Well, since VP is equal to 0, this is just equal to minus AOL times V sub n. And in this case, therefore, I can say that V sub n is equal to minus VO over AOL. So now that I know this, let's go and let's substitute for V sub n in this expression here. And if we do that, what I'm going to get is that Vs plus VO over AOL divided by 1,000 must be equal to minus VO over AOL minus VO over 2,000. And that's the expression I get. Now that I've done this, let's go and let's rearrange some terms. And I'm going to skip a couple of algebra steps here. But what I want to do is I want to group together all of my V sub O terms on one side of the equation. And so rearranging terms, what I will get is that VO will be equal to minus 2 over 1 plus 1 over AOL plus 2 over AOL times Vs. So after a couple of steps of algebra, I get to this. And now, let's let AOL go to infinity. What do we get? We get that VO is equal to minus 2 times Vs. So I get exactly the same expression that I got when I did the 3 rules and applied it to this circuit with 2K and 1K for my input and feedback resistors. So I'm still getting my minus 2, the same thing I got with the 3 rules with the op amp. Furthermore, looking at this, we see that over here, Vn is equal to minus VO over AOL. If that's the case and AOL goes to infinity, then Vn is just equal to 0 volts. So I've also got my virtual short circuit. Vn goes to 0 volts, the same voltage as Vp, and VO goes to minus 2 times Vs. So what we have here is exactly the same result. The virtual short circuit comes about because of the negative feedback and by letting that open loop gain term go to infinity. The expression VO equal minus 2 Vs. If we let the open loop gain go to infinity, we get exactly the same thing we got with the ideal op amp model. So it's always useful to point out that the op amp model and the 3 rules really come right out of just standard nodal analysis. The output is simply connected to this dependent voltage source, and then everything else follows from that. Okay? All right, now this points something out too. Notice both of these terms occurred because I assumed AOL goes to infinity. Now in real op amps, the open loop gain is not infinite. But what we find is this. In a real op amp circuit, In a real op-amp circuit, as long as the magnitude of the open loop gain is much, much greater than the magnitude of the closed loop gain. Then what we'll find is we can approximate the correct answer by using the ideal op-amp assumption. So as long as the magnitude of the open loop gain is much, much greater than the magnitude of the closed loop gain, we can use the ideal op-amp assumption to analyze real-world circuits, or I should say assumptions. So we can assume the virtual short circuit, and we can assume don't write a KCL equation at the output node, and assume the input currents are essentially equal to 0 for the op-amp. For practical designs, making those assumptions only results in a very small error from the ideal case. So that, or actually from the real world case. So as it turns out, that's why we're doing all of this ideal analysis, because the result will be close enough. The ideal assumption gets us very, very close to a real world answer. Okay? All right. So this is the inverting amplifier. You'll see lots of topologies based on this idea, and we'll look at a few more of them. Next time we'll look at the non-inverting amplifier, which is an interesting variation on this same topology we just analyzed.